One of the most difficult things about graphing rational functions for students is determining endpoint behavior. In other words, what happens to y as x gets infinitely big. We've looked at graphs that have 4 categories of endpoint behavior. Either they have a horizontal asymptote at y equals 0, means in the graph levels out at the x-axis. Or there's a horizontal asymptote but not on the x-axis, some other value of y. There's a slanted linear asymptote, or there's just a line with a hole in the graph. So I have 15 functions here, and in class we did a group activity where we had a card with each one of these functions and we sorted them into the 4 categories. There is one graph that actually ends up in both categories. It's different than anything you've seen in a homework problem, kind of a challenge problem. So if you look at the handout that goes with this, you could go ahead and try this activity first, sorting these functions into these 4 categories, and then turn the video back in and check how you did. If you'd want to just listen in and see how we do, this is how I'm going to go about this. So I'm going to look at the first one right here. What happens to y as x gets really, really big? Well, you can see this would be 1 divided by a really, really big number. Y would get close to 0. So this is one that has an endpoint behavior at 0. I'm going to skip over 2 for right now because 2 is actually a little bit tricky. And let's look at 3 first. What happens as x gets really, really, really big? So imagine putting, say, 1,000,000 in for x. So I would have 2,000,000 minus 3 over 1,000,000 minus 2. Well, think about this. As x gets really, really big, the 2,000,000 divided by the million would be dominate the graph. The minus 3 and the minus 2 isn't going to make much difference. So this would be like 2,000,000 over 1,000,000. So it's going to get really, really close to 2. So this is one where, I'm going to put that up here, where y is really, really, as y gets bigger, or sorry, as x gets bigger, y gets close to 2. So the asymptote is at y equals 2 instead of at y equals 0. Now I want to go back and look at number 2. Number 2 also goes in this second category, group 2, and it's because we also have, notice this is an x divided by x, and this is also an x divided by x. If I rewrote this as negative 3x plus 4 over x plus 7, you could see the same thing happening here. As x gets really, really big, the 4 and the 7 aren't going to matter much. Y is just going to get really close to negative 3. So y equals negative 3 would be the asymptote here. Now if you look at number 4 goes in category 1 because if x gets really, really big, we have 4 divided by a really big number squared. That's going to get close to 0. So as x gets really big, y gets close to 0. Now number 5 goes in category 2 because in this case we have an x squared divided by x squared. X squared divided by x squared is really close to 1. The minus 9 isn't going to make much difference as x gets really, really big. So this has a it has a horizontal asymptote at y equals 1. When we look at number 6, number 6 is a little different than what we've seen before, but it also goes in category 1. And the reason it goes in category 1 is because the denominator has a higher degree than the numerator. So when x gets really, really big, the numerator is the square of the numerator. It is a lot bigger. So think of 1,000,000 with 6 zeros, 1 with 6 zeros after it, and 1,000,000 squared, which would be a 1 with 12 zeros after it. Much bigger number in the denominator. And so as x gets really, really big, y goes to 0. Number 7 also goes in category 1. As x gets really, really big, the denominator gets to be a huge number, x squared. The numerator stays 6. So y is going to get close to 0. Number 8 goes into category 2. For the same reason number 5 does, we have an x squared over an x squared. Now, yes, there's a plus x here, and yes, there's a minus 2x here, But if we were to put a really big number in for x, these smaller terms would be so much smaller than the big squared terms that the squared terms are going to dominate. And once again, we're going to have y equals 1 because x squared over x squared would just simplify to 1. So looking at the highest degree terms, what happens to y? Y gets close to 1. Number 9, another one where we have an x squared term over an x squared term, but this time it's 3x squared over x squared, so y is going to get close to 3. Now I want you to notice what these four have in common. In every one of these, in the group 1, the denominator has a higher degree than the numerator. That's what makes the denominator get much bigger than the numerator, and y gets close to 0 as x gets really big. In group number 2, where we have a horizontal asymptote that is not equal to 0, in every one we have the same degree in the numerator and the denominator. I'm just going to abbreviate those, numerator and denominator, like this. So to find the horizontal asymptote, you take the highest degree term and you just divide those, and whatever you end up with is going to be the asymptote. So negative 3x over x is negative 3. X squared over x squared, 1. 3x squared over x squared, 3. 2x over x, 2. Okay, now the next 5 functions, the degree in the numerator is bigger than the degree in the denominator in each one of those. Degree in the numerator is bigger than the degree of the denominator. So if the degree of the numerator is bigger than the degree of the denominator, so I'm going to write this here, degree of the numerator greater than the degree of the denominator. It's going to either be in group 3 or 4. How do we tell the difference between group 3 and group 4? We have to factor and see if there's a common factor. So if there's a hole in the graph, we have a common factor in the numerator and the denominator. Otherwise, it's going to be a slanted asymptote in group 3. So let's start looking at these. If we look at number 10, we can see that if you factor the numerator, one of the factors is not going to be x. So clearly, this one does not have a common factor in the numerator and denominator. So number 10 goes in group 3. Number 11 ends up in group 4, and that's because you could factor the numerator to x plus 5, x minus 4 over x plus 5. So what happens is that f of x is just the line x minus 4 with a hole at x equals negative 5. So x can't equal negative 5, but otherwise the line looks exactly like y equals x minus 4. The third one, is there a common factor in the numerator and the denominator? Well, the numerator does not have a factor of x minus 3. It can be factored, but it does not have a factor of x minus 3. So this is a slanted asymptote. Now how do you find the slanted asymptote? Divide the numerator by the denominator. It will divide and give you a linear function because x squared divided by x in both of these cases would give you something with x in it. But there would be a remainder. That's the difference here. No remainder here when you divide. Here there'd be a remainder, but if you make x really, really big, the remainder gets closer to 0, and so the graph would just be the part of the equation that is not a remainder. So I'm not going to go through that process. You need to go back and look at example number 4 in the notes, or some of the examples in your homework for some examples of how you do that. Okay, so number 13 turns out to go in category 4 because there is a common factor of x minus 1. If you factor the numerator, it factors to 2x plus 1 times x minus 1 all over x minus 1. So when you cancel out the common factor, the graph is the line 2x plus 1 with a hole at x equals 1 because the denominator cannot equal 0 on the original function. Number 14 is an x cubed divided by an x. So if you divide x cubed divided by x cubed divided by x squared, you get x. So this does have a slanted linear asymptote. There are no common factors in the numerator and the denominator. If you factored the numerator, it would be x squared times x plus 1. And if you factored the denominator, you get x plus 2 times x minus 2. No common factors. The reason this one has a little asterisk by it is because not only does it have a slanted asymptote, it also has two vertical asymptotes. So it's kind of an unusual looking graph. Number 15 is in this category because the numerator has a factor of x minus 2 and the denominator has a factor of x times x minus 2, common factor. What's different about this graph, and the reason it has an asterisk, is if we cancel out the common factor, we end up with 1 over x. So we don't get a linear graph, we get a rational function, but it still has a hole. So we get the graph 1 over x with x equals 2 as the whole. So 1 over x also has a horizontal asymptote at 0 because the numerator has a higher degree than the denominator. So number 15 also is in this group, in group 1, because it has both a hole in the graph and a horizontal asymptote at 0. These 15 functions are the same 15 functions that are on the chapter review, study guide and review problems for rational functions. So you can, now that you've learned about their endpoint behavior, you can go ahead and practice actually drawing the graphs for these and see how the graphs work out as well.